So, before I start the lecture, I want to remind you Tuesday we'll have lectures replacing the lectures that we have missed during the strike in room 301 from 7 till 10 on this Tuesday, from 6 till 10 next Tuesday. So we'll have the same format as we are having now. So will be recorded, of course, but if you can personally take part in it, it's more advantageous. Probably you'll learn more. Okay, so basically we are in this lecture intending to go into one of the most celebrated result of condensed matter physics or solid state physics, which is the behavior of electrons in a lattice. In the previous lecture, we took some time to prove Bloch theorem. We proved it in two different ways. One of them was by translation operators, which was a very elegant way to show it, and the other was through a Fourier transform, which gave a feeling of being a bit cumbersome. And then some of you might question, why did we bother? We had a perfectly good proof with the translation. Why did we need another proof? That was actually to give us the background to the current lecture, because once I know to write the Hamiltonian of potentials that has a translational symmetry, meaning a lattice, then I can much more easily try to solve it, and solve it in the meaning of not necessarily writing down a potential and solving the Hamiltonian for a specific potential. That could be very interesting if you are trying, for example, to study the properties of a certain element or a certain lattice. You want to know what is the conductivity in copper. You need to know the specifics of the material. Here our aim is to get a more general overview of what types of behavior emerge from the mere fact that I have a potential which has a lattice structure. And for that, writing down the Hamiltonian as a Fourier transform gives me a very convenient tool to do it. So what we are doing today is finishing some tidbits out of chapter 8 in Ashcroft, and moving on to the nearly free electron description of chapter 9. Let me rewrite the Fourier transform of the Hamiltonian. Okay, so that's a Hamiltonian. We developed it in the previous lecture, but let me stop a minute to consider the properties that we see here. Okay, so this is a Hamiltonian, or actually the Schrödinger equation would be more exact. And let's note a couple of things. Is this a differential equation? No. Why isn't it?
Fourier transform.
Because we have Fourier transformed the equation. So we have actually a linear algebra type of equation. These are the Fourier second. So we have here some connection between the Fourier transform, a specific Fourier transform amplitude, to basically an infinite number of other Fourier transform amplitudes. Okay, second, and here I deviate a bit from the notation appearing in Ashcroft. This is a reciprocal that's a reciprocal vector of the lattice. Now, Ashcroft actually uses large K, but small k's and large k's with my handwriting on the blackboard will create infinite confusion here. So I'm changing it to large G. Okay. What is small k?
Wave vector?
Excuse me?
The wave vector?
The wave vector, the usual wave vector, which, if we have periodic boundary conditions, has a quantization of pi over L, the size of the boundary conditions, size of the sample. This, on the other hand, has a scale, so I write it down very inexact but useful to keep in mind. K behaves like 1 over L. On the other hand, this guy, how does it behave? As here, I don't care at the moment about 2 pi's.
If it's the reciprocal, no.
If it's a
reciprocal lattice, but
exactly, it behaves like 1 over A. It's much, much larger than small k, typically. You still have an infinite number of them, but you have a lot of these guys in between each of these guys.
רגע, מה זה?
A is the L, the size of the sample. So I'll draw it here. This is A and this is L. So as I said, 1 over L is much smaller than 1 over A. Okay, what else should I note? This is a potential. This potential is a Fourier transform, but only with reciprocal lattice. Why? Because the potential has a periodicity of A. Has to return to the same value at each point, which is different just by large R, the lattice vector. Therefore, the Fourier transform has much less G components than K. Okay, so these were general aspects of what do we know about the equation. Now, in reality, if I want to solve a specific potential, I have to know what's U as function of R, perform the Fourier transform, stick it here, which is basically a large matrix, and go solve it. Sometimes, especially if I have a good computer, it's a way to go. But here we want to actually study specific properties of this guy, and for this we'll try to get very general results out of delving into this Schrödinger equation. Okay, so I told you that I have still a few bits and pieces to say about the properties of the Bloch wave function. Okay, so that was a conclusion that we proved two different ways in the previous lecture. Okay, this is a periodic function. This is a phase. And now I would like to examine a connection that is deeply rooted in our understanding of quantum mechanics. And this is the connection between momentum and K, the wave number, the wave vector. You are using this connection nowadays instinctively, I hope. Is this correct for our Bloch wave function?
It's supposed to work. This is the right form we use in for plus, doesn't it?
So the answer is, why should it?
It's not a free particle.
It's not a free particle. All our intuition about the connection between a wave function and the momentum comes from free particles. This is not a free particle. Therefore, I should check it. Okay. Let's see what, using the operator that we usually use for momentum on the wave function gives us. Simply performing the derivative.
Is it H and purpose and not beta?
Excuse me? Here is H. Let's get so used to write H bar that automatically. Okay, nothing beyond simple derivative. This is what we expect. This is something different. We have some correction. When will it give me the expected behavior of a free electron?
If the second part is 0.
No, if the second part is 0, and when is that?
When you have 2 pi.
When U is constant, correct. Which is the free electron solution. But if it's not a free electron, it's not necessarily correct. Okay, so nevertheless, can we get some connection between momentum or velocity and some other property of the system for the Bloch solutions? The answer is yes. And the connection, and I'll prove it in a minute. So this is the velocity which we know already is not simply h bar k over n. So the gradient of the dependence of energy on K. Which reminds you something that you have seen in waves. What does it remind you?
Group velocity?
Exactly, group velocity. Okay, let's prove the statement. What happens to the energy when I change K by a bit?
Taylor expansion.
I'll do here a Taylor expansion.
What epsilon means?
Excuse me?
What's the function epsilon?
Energy.
Energy?
Okay, let me write it down. Because this is not physics, this is just mathematics. Okay, from where do I get the behavior of E?
The Schrödinger equation?
Of course, the Schrödinger equation. Or, if I apply the Hamiltonian, on the energy eigenvalues. What did I do here? What is the only non-trivial step here? What is H? The Hamiltonian.
That you make a powered by that disappear. You made all the exponent vanish. That's what you did there. Is it?
Of course, I killed the exponential. Perhaps I should have written it in 2 steps, it would have been more clear. This is the Schrödinger equation. So I'm going and performing the derivative, and since the derivative I have here a double derivative of an exponential, I get what's written here. Nothing beyond that. You remember that all the time there appeared here an n, and it should have bothered you. From where does this n come?
The n from the index quantization.
Okay, but I have k.
You have 2 indexes, one for the solution and one another for...
Exactly, I have the k writing down the Bloch theorem, and here I have a differential equation that can have n solutions. That's the easiest way to understand from where this n comes. A different way is basically you have put your case in a Brillouin zone and you have infinite copies of them. But I think this is much clearer and immediate.
So there's a different quantization for K and for M. That's what you're saying.
No, it's 2 quantum numbers.
Yes, okay.
The same if you want to think about it. When you go in, well, question if you did it. If you go from a situation where you have one K, let's say, and put it in an harmonic oscillator, you get many N's, right? Now, well, that you'll see even more clear in the next lecture, perhaps in 2 lectures. I can actually start my systems this way. Put solutions of single atoms and put the atoms one connected to the other. And then it would be even clearer. But here it's just the results of mathematics. Okay. Why did I do this step? Because I want to know something about EK. So this, what is special about the differential equation written here?
Linear?
All of the equations in quantum mechanics are linear at this stage at least. It's an equation that depends on k. It's an equation for a specific k. Okay, what happens if I write it down for k plus q? Okay, let's see. Okay, then instead of what's written here, I'll have and k will be replaced by k plus q. Okay. And this will be, of course, equal to ek plus q times.
Why is there an h bar divided by 2?
Oh, sorry, my mistake. I should put it twice. Okay, q is small, so I'll use that fact here.
Do the expansion of it?
I'll do an expansion of what's written here and throw out terms of order q squared. Okay. I just wrote down the terms of this plus this. For small q's,
Minus or plus to 2q.
plus, of course. Okay. Okay, so that's the energy. The first term here, plus u, what does it give me?
The energy epsilon k.
This plus this,
So the original epsilon k k.
right? So I write down explicitly the matrix element that's written here. I want to keep this because this is what What should have disturbed you? I'm missing here something. Right?
What are the limits of the integral?
Well, I could have told you from minus infinity to
Not the
infinity,
optimal values.
but who? But since each cell is the same as any other cell, I can integrate over the cells.
Multiply by the number of cells, or?
let's compare it to what I've just erased. I'll just rewrite it here. Which was just the expansion of E at K plus Q compared to E at K. We did it a few minutes ago. Didn't write it this way, we wrote it as it has the same meaning. Okay? So, this part is equal to this part. Here I have Q dot something. And here I have Q dot something. So the two somethings describing EK plus Q have to be equal. Meaning, all I did is copy the two terms and equate them.
What are we?
Excuse me?
What are we integrating here?
Remember, U of nk depends on R. This is a derivative by R. Remember the Bloch theorem is psi of nk is equal to e to the power ikr. You already see that it's a function of r times unk, those are quantum numbers, and nk as a function of r. So the integration must be on r. Okay. If you don't believe me, just put in the definition of psi. Perform the derivative and you'll get back to here. Definition of psi according to the Bloch theorem. That up to an h bar is the definition of Vn. Proof of what we have written here. Okay.
What about the mass?
Remember, it's velocity. And in the
Okay.
definition of velocity, you have to
It's the momentum of the mass.
you divide by n. Okay, I want to keep this part still on the board, so I'll remove this. This can also go. So I have here my Schrödinger equation. What is a solution for the tremendously difficult case where u is equal 0?
It's a wave, free energy, free electrons.
Okay, we know that already. Right?
Yeah, we said it before.
So if this is equal 0, we have only this term equal to 0. Okay? And the spectrum in this case won't surprise you.
eigenvalue equation?
Mm-hmm. And
One here is a scalar, one here is a vector.
vector square is a scalar. If that bothers you, you should have been bothered long time ago when they told you that a free electron's energy is h bar squared k vector squared divided by 2n. It's the same equation. That I call it C and not psi, who cares? Right? But there is a point that should disturb you. And it's actually a deep point that one has to think about it carefully. Look, if I didn't go through this whole procedure and just solve the problem of free electron, right? Didn't do anything.
There's no G in the solution.
There's no G in the solution. Then you can stop and tell me, what do you care that there is a G? That just has a translation in the origin of K, right? But it's much more than that. Let me just plot this solution as it's given here. So this is K. And this is E. So it's simply k squared over 2n. Let's take another reciprocal lattice. For simplicity, I assume one dimension just so I can plot it. So I'll have here a point. And in a one-dimensional case, I can give you a simple where it is pi over a. Right? So that's the first G. This guy will still be a parabola, but a parabola with k could have such a solution. Here, minus pi j. And I think I'm out of colors, but can imagine that I'll have more and more and more solution, an infinite number of parabolas. From where comes this infinite of parabolas? I solved it as a free energy problem. I had just one parabola. I solve it as a lattice problem and set u equals 0. I have an infinite number of parabolas. Right? Physically, I take my potential measurement device. I see u is equal 0, and I can't decide what is the correct solution. Right?
What does it? Depends on the choice of a lattice point and a choice of a wave vector. But each particle only really has each particle has both position and a wave vector.
Okay, so.
That doesn't change the fact that
There's no potential.
Right?
they're
I wake up in the morning and I decide I'll solve it as a free electron. I get solution 1, just this parabola. I wake up in the next morning, I decide, no, I want to solve it as a lattice, but then take the potential to 0. I have another solution. Doesn't make any sense, right? Actually, we met such a situation in phonons. Remember when we had a lattice with one particle per lattice, and we got a solution. And then we decided, no, I want to, although those two particles are the same, I want to call my lattice cell 2 particles per lattice cell. It's my choice. It's my freedom to do it. And you remember that I got this doubling of the solutions. And it clearly can't have a physical meaning. What is the solution? Well, you are free to choose any way to look at the system, because the ways that it's like defining point of origin or defining some kind of coordinates to describe the system. It's your prerogative to choose whatever you feel like. But if you choose, you have to understand what is the meaning of your choice. So, if I'm choosing as a free electron, okay, go look on your blue parabola, get a K, return a value. Okay, give me a K, I'll give you an energy. In this case, I'm telling you, excuse me a moment, if you chose to address the system as a system with a lattice, fine with me. I'm not allowed to tell you it's not allowed, because it is allowed. But then pay attention. You should check what is happening in the first Brillouin zone. If I'm talking an unfamiliar language, go back, we did it a couple of months ago. What is a Brillouin zone? That's the zone and then you have n equal 1, n equal 2, and so on and so forth. If you are just ignoring this fact and just drawing all these parabolas, you are doing not a double counting, you are doing an infinite counting of your numbers. It's fine to talk about k in the Brillouin zone and using n to number them. So k in this case goes only in between. That's that. You want to talk about something that has no lattice? Fine, go and talk about the blue parabola. Okay, so first of all, from the point of view of mathematics, just choosing the language changes the way that you number the wave functions. It doesn't change the physics, it doesn't change the results, but it changes the way that you number.
So we still measure the same energies for all these real electrons, but so what happens when I measure an energy that is on one of the higher parabolas? What does that means that I might have two. So what that means the quantum number isn't one.
Right, the quantum number is 2, and when you are looking at quantum number 2, you take this branch and move it out by a g.
And but just free electrons only has one quantum number, the k.
Right.
And then
because
in the lattice we have another quantum, another number, right?
Right. So what happens here actually?
There are two solutions.
No, it's just you're counting them differently. You decide that k goes only between minus pi over 2a and pi over 2a for the one-dimensional case, and I'll keep it in this lecture only in the one-dimensional case, because life becomes complicated once you're looking on 2 and 3 dimensions. If Ashcroft is full with nice drawings of the Brillouin zone for higher dimensions, but and if you move to n equal 2, you can add either use this form and just move this part into the correct part of the parabola and use k, or decide that no, I can't just simply put k square, I have to take into account that you are now in the, well, I'll introduce something that I didn't define yet. I'm in the first band, in the second band, in the third band, and so on. You have to tell me, you want to talk about the lattice? Fine, but tell me in which Brillouin zone I'm sitting.
So if I want to find the energy in a K that's outside the Brillouin zone, I just move it by G.
Right? By the appropriate G for the n equal
2 pi
2 pi times
part divided by A.
right? Okay.
And you measure only between minus pi divided by 2a to pi divided by 2a. This is all settled. Like all the blue parts outside of this are not relevant, you know.
Well, they are relevant. They are just translated into this region.
So you put in back. Like
You
we did
fold
before.
it. It's called, technically, it's called folding into the Brillouin zone.
Yeah, but this. So they continue only until pi divided by a.
And then the means this way.
Okay.
Okay, this is a hard concept, and hopefully you'll get used to it. But this is a very important concept here. Perhaps the most basic concept that we have in electronic states of a lattice. Okay. What is the wave function?
Characteristic.
Which is, of course, a free unit. Okay. So this is one confusing point that will come back to bite us all the time, and we have to pay attention to it. Okay, but in the end of the day, we didn't come here just to work out the properties of representing the wave function as a free electron or a free electron with a lattice that has zero potential. For that, it's a complete waste of time. You want to consider the case where U is not equal to 0. And there are two approaches how to get into this problem. And we'll see that basically they describe, both of them describe different limits. It's known as the free electron, nearly free electron.
Perturbation theory?
Mm-hmm. Both of them are perturbation theory, but what is a perturbation is the difference between it. We are already in the stage in our physics studies that either we can apply perturbation theory and say something, or we can't and we are unable to say anything. String theory didn't predict anything because you can't use it. No one knows how to apply a perturbation theory. QCD can give us only some numerical results under certain conditions. Again, QCD is very hard to do real perturbation theory.
But isn't QCD have a different approach, lattice something?
And how do you solve lattice chromodynamics? On a computer. This, I have to say something not to make it. What is the difference with QCD? Asymptotic freedom. When the particles are close, they have almost no interaction. When they start to move away from each other, the interaction grows. Very strange against any. Well, why is, okay, it's in the Hamiltonian of QCD. Show me it. The proofs are very iffy. you can write a phenomenological model which tells you, believe me, that's actually what the Hamiltonian describes. And then you can get results and compare it to experiment, and works quite well. But this leap of prove it. No, we can show you some numerics that seem to indicate that this is indeed the behavior. Prove it. And why you can do perturbation? Because perturbation is built on that gets the particles to infinity. They don't know about each other. And here it's the opposite way around.
Infinity, they attract each other.
Right. Don't have a good point to start your perturbation. There's also some problems in classical and quantum physics like solitons and things like that, which are hard to tackle exactly because you don't have a good perturbation theory. But here we are starting for two approaches that are very different. So we start from free electrons. And we apply weak U and solve it. The tight binding approach which here we start from we take independent atoms. We know that they have quantized levels. Think about the hydrogen atom. And assumes that the atoms are not infinitely far from each other. Those two very different approaches, one looking on a free electron and asking what happens if I put in a very weak potential, periodic potential, what happens to the energy and the wave function. And the second, we can think of it as conceptually the opposite limit. We have atoms, we have potential wells which are deep, and basically the electrons sit very tightly bound to these wells. That's why tight binding. And we put another well far away. And we know that there's some tunneling between them, which causes the electron to spread out. Seems two different approaches, and what's nice about it, it gives you the same physics. Doesn't matter from which end of the possible models you start, you end up with essentially the same model. And once you end up with the same model, you know that you captured the behavior, and maybe you got the details a bit wrong, but the general behavior is solid. Unintended. Okay, so let's start. We have 10 minutes, but 10 minutes should be enough to get the first result here. Let's choose one of the G's here. Okay, what did I do here? Call this part epsilon 0k minus g. One chose a particular value of g, and just wrote the equation. This part didn't change, and here is what is appearing here.
I don't think it really matters, but the order of the u is supposed to be g1 minus g, I think.
I prefer to write it this way for the... Just a moment here. Why?
In reference point.
No, I'm writing
But you sum over g tau.
here. Oh,
So it's supposed to be g1 minus g?
oh, you're talking about the second.
Yes.
And please answer.
It doesn't, I said I think it doesn't matter
Why?
because g isn't dependent on point.
The distance between A and B,
Yeah.
that's between B and A.
Because we showed, I think, a couple of lectures ago that u of g is equal u of minus g, so it doesn't matter. Because at the end of the day, because u is a real number, it's a potential. So u and u complex conjugate is the same thing. And the only difference in a Fourier transform between a value and minus its value, it's the complex conjugate. But here, u is a real number, so it doesn't matter. Okay. Lovely. How do I solve it? Well, I observe that this guy at a certain G1 depends on all the C's include that are not necessarily at G1. Okay, let's see what would be the equation for a guy that's not at G1. So for G prime, let's say, not equal G1, all other G's. What is the Schrödinger equation that describes these C's? Okay, the same, basically. So, I want to separate this summation to G equal G prime and all the rest. So I just separate it to the first guy and all the other guys. G minus prime should be here, and here should be a G prime. Prime, and here should be a G prime. Okay. Okay, what do I see here? Why did I do this whole exercise? I want to take this guy and return it into here in order to close this self-consistent equation.
בראש חסר שם טאג על ה-G של ה-C במונה או שם. שרשמת. במונה. השורה האמצעית שם. שרשמת.
This is J1. Plus G. This was a mistake. Here it's G1. Okay, so what did I do here? I want to find out what should I enter into the equation for all the CKs that I have here. Right, so one of the guys I know, it's the G1 itself, no problem. And what should I add in? All the other CKs, and that's what I have written here. And now, how do I cut off this infinite chain? How I write down a perturbation theory?
Expand something in a Taylor series?
No, I've already expanded.
So compare powers?
I'm looking at the values of u. Remember, u is a small parameters. Here I have 1. Right? Here I have 1, but these guys have to go into the chain again, which will give me a power u to the square. I use only this part and throw out the rest. And when I do it, you'll actually see a solution that will immediately jump to your eye. Okay, so let me just... So I'm continuing here. I'm just taking what's written here, E minus E0 K minus G1 times C K minus G1 equal, and sum over G U G minus G1, and enter And what is that? Second order perturbation theory. Just a result if we would have simplistically enter the result of the second order perturbation theory.
What about the first order?
Just zero. Okay, we're a bit running out of time, so we'll discuss what this actually means in the next lecture.
So how to do this?